So hello everyone. I'm Filip, representing University of Zagreb, and I will explain you our decision support tool, how we did it and how it works. More importantly, but before the tool itself, a few words through a presentation of uh, methodology and motivation for the tool itself. So we all already know why are we doing this. Of course, the main point is renewable energy. So as we get more and more solar and wind, intermittent sources, and also intermittent high consumption like electromobility, and then also hydrogen production, we get stress on our network, our electricity grid. So energy systems are becoming unprecedentedly dynamic in market and technical terms. And one of the ways to balance them is, for example, using electricity storage. But electricity is not easy to store. So maybe we can use some flexible demand, flexible consumption of this electricity. One of these ways are so-called renewable energy hubs. So these are energy systems that are with years becoming more and more complex with more and more components to it. But they can help balance the grid because in design they are flexible, so they can change when they produce and when they consume energy, because they are effectively energy storage systems. They are named renewable energy hubs because, they deal with renewable energy. But if they are based on hydrogen, like in our case, they could be also called hydrogen hubs. And so our decision support tool is for investments in these renewable energy hubs or hydrogen hubs. On the image, you can see some of the technologies that we use in the tool that you can use for sizing and operation planning. So the tool, what it does, it answers some of the questions. For example, what set of technologies to use? It tells you whether to use electrolyzer, which electrolyzer to use, wind farm or PV plant or batteries, yes or no. It tells you what should be the sizes of these components. So how big the solar plant should be, what should be the capacity of this storage system, how big the electrolyzer should be. And the tool also tells you how it all should be operated. For example, when should you turn on or off the electrolyzer and with which power. And it takes into account all the dynamics, all the market, because electricity prices can change every hour or even every 15 minutes, and the sun is changing all the time. So in all those dynamic environments, the tool finds the best solution. So in short, the tool tells you how to size and how to operate this renewable energy hub. And these two operations, so sizing and operating, are dependable decisions. So you cannot, you could first determine what should be the best size and then determine how it should be operated. But if you do it separately, you will not get the best results. It's not the optimum. What we do is we optimize all at once. So we get the real optimal value for each of the components, and how should they be sized and how should they operate throughout the year. So the concept of the tool. So this is let's say a diagram of technologies, components that are considered in the tool. Of course, there is connection to the electricity grid. We don't consider off-grid system, just connected to the grid. We have renewable energy surplus. As Mattia showed us, you can use the output of the hydrogen potential model. I put it here as an input. You could have already existing local renewable energy plant, or you can build a new one, either a photovoltaic plant or a wind farm. There is battery energy storage system. There is maybe some fixed consumption of electricity. It could be tied to an industry. And there is the right part, which is all about hydrogen. Producing it by electrolyser, or rather consuming it by using fuel cells. Also, we consider using waste heat from both the electrolyser and the fuel cell. And there is also byproduct oxygen. And all this we can model with our tool. So the key here is modularity, because eventually you get several applications in just one application, because you can use maybe only electricity. Maybe you want to size a PV plant and battery for your house. You can use it just for that, or any other combination that is physically possible. You cannot just have waste heat if you don't have electrolyzers, for example. Then there is collaboration. Well, you can merge multiple projects, synergies within each other. So we can use inputs from other projects in this tool as well. And also for future proofing, this modularity leaves space for integrating innovations. Like, for example, in the future, we might also need some new component, some new technology that might be viable, that is on the market, and we could just simply add it into the tool along with the rest of the components. For example, what would be done? This is an example from our ongoing projects from Inter-Danube region. For example, to use waste heat. We include some, but it could be further developed. For example, buildings can be great users of this waste heat, and not only fixed consumption, where you must have also some thermal energy storage. Maybe you could smartly operate this building through data-driven approaches, and this building becomes flexible demand for heat, so you can use more heat with less capex. So HyEfRe decision support tool application, what we call is joint sizing and operation planning of hydrogen-based renewable energy hubs. So far, we made 2 tools for different technologies. A simpler one for only PV plus battery systems, or some more complex, combining biomass and digestion and electrolysis and methanation, and doing more with methane. And in parallel, we are creating different but similar applications for a few different projects, EU projects, but they're all focused on hydrogen. So how the tool works and how to use it. So the tool, of course, has its own graphical user interface, and it is application that is downloadable on the computer. It's not a web-based application. And inside it has data that you can choose from, or you can enter your own data and then optimize your scenarios. And now I will show you how it looks like. Some general workflow is to pick technologies you are considering from the full technology setup. Then you set market conditions. For example, that would be demand and prices, how much hydrogen could be sold or needed, and what would be the price. So you set the technology parameters on your own, or you set defaults from the tool. Then you press run optimization. And then after some time, after the optimization is finished, then you analyze result. And then let's see how it looks like. So I already opened the tool. So this is like a landing welcome screen. And then what we do is create a project, because the application is project-based. So let's say we create a new project. We call it, let's say, my project. It doesn't matter. And then we would start modeling with our tool. So here on the left side would be your list of scenarios. So for now, we don't have any, so we'll add a new one, scenario 1. And then we click on system structure. This is the place where we have the most of interaction with the tool. And now in the main window, now we see our technology setup. So this is the diagram you've seen from the presentation, but it's not full because not all components are active. Here with these checkboxes, I can choose which technologies I would like to use or not. Why not to use all? Because the tool can say, if I use all, the tool can say, maybe don't use this one. It can say the optimal size is 0. But in that case, you would need to know all the parameters for each of the component, which is not so easy sometimes. And it's computationally pretty expensive. So for an example, let's imagine we have an industrial plant which has its own electricity consumption. It has its own electricity grid connection, and now it has also a lot of roof for PV panels, and it has ability to produce hydrogen and sell it on the market. So we need this electrical grid connection, but other things I will remove. So we have a power PV plant. We have, let's say, we could have a battery storage system, electricity consumption, of course, electrolyser, selling hydrogen, and that would be it. Let's say like this. So we have electrical part and the hydrogen part. And now we enter parameters. Now simple is location. Let's say it's in Zagreb, in Croatia. You can simply choose the municipality. There is a list from all the Interreg Central Europe countries, or you can choose on a map. Then we need some parameters about electrical grid connection. Luckily, we have our countries with data already inside. So about the grid connection, I can just simply choose one of the existing connections, and all the parameters are already entered. And since it is an existing industry with its own existing connection, I can choose that the connection exists, and I will enter its size. Let's say it's a 1 megawatt connection. Then we need parameters on electricity supply. That is electricity prices and feed-in prices and the times of high or low tariff. So you can generate this, you can enter data here, or you can use a custom profile. For example, if you want to use prices from day ahead, like I have in a folder. So I have a CSV file with day ahead prices. So I will choose these prices and import this data. I have also this button, so I can check the data. So I can check if the data is fine. I can zoom in or out, and then move on. Then from PV, I can have multiple arrays. So every array has a different angle. But let's say we have a field, and we would put panels towards the south and inclined 30 degrees. And we know we have, let's say, 30,000 square meters of available space. Then the battery energy storage system, we could enter parameters, but we can leave it as is. We can use default parameters. You will notice in the tool, there are sometimes called advanced parameters, which could be modified, but not necessary. That this part can be left as is. Electricity consumption, I already said that it's an industry with its own consumption. So I will enter here consumer. I call it industry. And then I can either import data if I have an exact profile, 8,760 values, or I can generate it because we have different generic profiles already in the tool. And let's say it's a warehouse, and we just set the one number, which is total annual demand. and then the tool scales this profile, which can be also checked with this button. Then we define electrolyzers. Notice it's a plural because we can have multiple electrolyzers, but for now we will just add one. Electrolyzer 1, you can enter all the parameters or just choose one of the following, let's say generic electrolyzer. Water supply we can skip because the data is already entered. And then we have hydrogen sales, which is very important because here you define the demand for hydrogen. And you could maybe have a number of customers. So I will add one customer and define its parameters, its demand. So the tool can also differentiate between green and non-green hydrogen. So here you can check whether this customer wants green or non-green hydrogen. Because let's go back to the diagram. You see, we have a PV plant, which is a source of green electricity, and we have electrical grid connection, which is source of non-green electricity, because it's an energy mix. So it could be green, but most probably it's a mix of everything. But let's say this customer wants only green hydrogen. And then let's define demand frequency daily and mass of 350 kilograms. So this means that the customer wants 350 kilograms per day. And for the price of 5 euros and pressure of 450 bars. So that would be our demand defined, and I will just define some simulation parameters just quickly. The idea is to have a simulation that lasts for a full year, because then we have the best results, but it will take a long time. And for this demonstration purposes, I will shorten this to 1 month. So let's say we just scale it to April. So that would be some kind of middle ground for the PV production, not as much as in the summer, but not as little as in the winter. And I will choose a different sample time. Now, when I have all the parameters entered, I can click Run Optimization, save, and then we wait for the optimization to finish. This should be rather quick because I chose 1 month rather than 1 year. And once it is finished, on the left, under this scenario, there will be a new page that you can click on called Results. And it should be any moment now. Yeah, it's always like this. When it's a presentation, it takes longer. Okay, here it is. We have the results. So this is the results page. There are some tables, there are some charts, and you can look around and see what we have here. First, let's see what we get. So the recommended, what the tool says it's the optimal, could save or rather generate 800,000 euros in 20 years, and the payoff period would be 18 years. So not short payoff period. We have parts in the results like key recommendations, how much of PV plant, battery storage, how big the electrolyzer should be. So let's say this is 50 kilowatts grid connection that was already existing, no need for any improvement. Then we have some financial indicators like total capex, opex per year, total yearly revenue. That is all taken into account, all the maintenance and degradation of the components, all the cost of electricity, cost of grid fees, and the revenue from selling hydrogen. There are some financial indicators like payback period, net present value, levelized cost of hydrogen. So at 3.56 euros per kilogram, it will be break even after 20 years. Since we put 5 euros, we we have payoff of 18 years, not 20. And then we have operation. You notice this is only April because that's what I said in the parameters. And it's these charts are dynamic, so I can scroll, I can zoom in, move it around, and I can remove some parts because it gets noisy. It's hard to see what is going on. For example, if I choose, I want to see fixed electricity consumption, that's what the industry uses. And then I can also, let's say, put PV, it's much less. And I can maybe see what the electrolyzer is doing. See, electrolyzer, the orange one is much less than the fixed consumption. And we can see that electrolyzer is producing hydrogen only when there is plenty of sun shining. So only when we have PV production. Then we can see hydrogen production and hydrogen sales. Hydrogen production goes up and down because of what we've seen because of PV production. And then, but the sales are pretty uniform. This is because we have hydrogen storage that can serve as a buffer between production and sales. And then we have amount of hydrogen in the tank throughout this time. And then we have detail investment, detail yearly, more detailed stuff for the battery and capacity factors. For example, electrolyzer works about 35 capacity factor because it's not all the time. And from here, yes, you can build reports from this, or you can dig deeper and you want to know what would happen if I change some parameter. So if I go back to system structure, this button run optimization is now gray. I cannot click because the optimization has finished. We have already results. And if I want to change something and run again, I can go and right click on this scenario, duplicate it, and then change something and run it again. So let's say I want to check if I have some subsidies. Let's say 30%. I can click run optimization, save, and now the tool calculates again with all the same parameters as before. So I don't need to enter all the parameters from the beginning because I already have them. Enter in the first scenario, and it should take roughly the same time. And then we can, when we get results from this second scenario, then we can compare the results. So what to look? Let's look at the first sentence. The payoff period would be 17 years. Remember, before we had 18, so not much difference. But the amount of savings or generation of euros, before we had 0.8 million, and now we have 7 million that we could generate in 20 years. This is only with 30% subsidy for investment, because we have much larger PV capacity. Before we had 500, now we have 4.5 megawatts, much bigger battery, much bigger electrolyzer, and so on. Of course, investment is much more, but eventually we earn more. And if we take a look again at this chart, let's say PV, only PV and electrolyzer. Again, we see the orange line is electrolyzer. It is producing only when there is enough electricity from the PV. For example, the days when there is much less hydrogen production. And then you can compare these results. Of course, you can save this project, and if you close it, you can open it again and continue working with this tool. So that would be shortly how the tool should be operated, how we envision it. And since there is a lot of parameters, it's not a simple tool. It is pretty powerful, can do lots of things. We made user manual of the tool. It is not yet released, but I can show you how it looks, how it will look. It will actually be a website. So you can go on the website and scroll through it to find what what you need. And you have also search, so you can search for yeah, what you want, because let's say example, here you have simple example where you have steps to recreate something similar to what I just did, with screenshots and explanation how it works. And of course, we have explained everything, all the parts of the interface and all of this system structure. So component details, there is part for every component, and every component is explained, and also every parameter. So it's quite long, but you have a search bar to find what you really need. So that would be all from my side. The tool is not yet released to the public, so if you're interested, please follow project website or LinkedIn, or contact us via email, and we will send the tool as soon as it is finalized and released. If you're really interested, we can send also the tool as it is now in some sort of alpha version with some minor bugs still waiting to be resolved. So yeah, thank you.